Let us look at a new technique, that is differentiation under a definite integral, also called the Leibniz rule. So here, differentiation under an integral is a powerful technique used when an integral depends on a parameter and we want to differentiate the entire integral with respect to that parameter without first evaluating the integral. So here, let's say we have an integral I of alpha equal to the integral from a to b of f of x comma alpha dx. So here, this integral not only depends on x, but it also depends on a parameter alpha. Now, f and the partial derivative of f with respect to alpha are continuous in both x and alpha. Then only this technique will be applied. So what the Leibniz rule says is di by d alpha is equal to, that is a derivative of the integral with respect to alpha, is equal to d by d alpha of the integral of f of x comma alpha dx from a to b is equal to the integral from a to b of the partial derivative of f of x comma alpha with respect to alpha dx. So here we have differentiation and we have an integral. Now, instead of trying to solve this, what we do is we do this. We take the differentiation, more specifically a partial differentiation with respect to alpha under the integral. And by the way, here you will notice that a and b are independent of x and alpha. So that's why this particular one is called Leibniz rule for constant limits. A more general one would be I of alpha is equal to the integral of f of x comma alpha dx from a of alpha to b of alpha. So the difference is that here the limits are also functions of alpha. Or in other words, the limits depend on alpha as well. And the formula for this is di by d alpha is equal to f of b alpha comma alpha. That is the function value at b of alpha comma alpha times the rate of change of b with respect to alpha minus f of a alpha comma alpha times dA by d alpha plus the integral from a of alpha to b of alpha of partial derivative of f of x comma alpha with respect to alpha dx. And this is the general Leibniz rule. Now here, if we take a of alpha and b of alpha as constant, instead of it being dependent on alpha, we just say a and b, which means that rate of change of a with respect to alpha and rate of change of b with respect to alpha would be 0. There is no change in a or b with respect to alpha as alpha changes. So that means they both will become 0. That means the first two terms will disappear and we are left with the third term only. And since a and b are independent, we will just have a and b as the limits. Now let's look at an example. D by dt of the integral from 0 to 1 of 2x plus t cube to the whole power 2 dx. Now let's very briefly plot this and see how it looks. So the function is this. Think of it like this. If t is equal to 0, it becomes 4x square, right? Which is a parabola. Here the limits are 0 and 1. So we are interested in the area under the curve from 0 to 1. Now, as the value of t changes, what will happen? The parabola shifts. I'm going from -5 to 5. So we want to arrive at the area under the curve. Okay, let's see how to proceed. Now here you will notice that the limits are constant. That means we are going to use this formula. d by dt of integral 0 to 1 of 2x plus t cube the whole square dx is equal to the integral from 0 to 1 of dou of 2x plus t cube the whole square by dou t dx. Dou stands for partial derivative. Now let's take care of this partial derivative first. So partial derivative of the function with respect to t is equal to 2 times 2x plus t cube times dou t cube by dou t, which is equal to 2 times 2x plus t cube times 3t square, which is equal to 60 square times 2x plus t cube. Remember, we are differentiating with respect to t. That is why x is treated as a constant. And the differential rules are applied to t. So our d by dt of integral from 0 to 1 of 2x plus t cube the whole square dx is equal to the integral from 0 to 1 of the partial derivative, which we have arrived at 60 square times 2x plus t cube dx, which is equal to 60 square is constant, we take it out, integral 0 to 1 of 2x plus t cube dx. Now let's take care of this integral. So 60 square times x square plus t cube x. Because remember, we are integrating with respect to x from 0 to 1. And carrying out the necessary substitutions, what will happen? We will get 60 square times 1 square, that is 1 plus t cube, minus, if we substitute 0, these two terms become 0, so the whole thing becomes 0. And opening up the bracket, we get 60 square plus 60 to the power of 5. So we have seen that with just 4 steps, we have arrived at the solution. So this was the case where the limits were constants. Now let's look at a case where the lower limit is constant, but the upper limit varies, is a function of t. Now let's look at the next problem. Here, if you will notice, it looks like the same problem that we saw just now. But the difference is here, lower limit is 0, upper limit is t. In the previous example, we looked at the lower limit was 0 and upper limit was 1. So here the upper limit is a function of t. So let's see how this works out. So a of t is equal to 0 implies dA by dt equal to 0. P of t is equal to t, which implies dB by dt is equal to 1. And now, since we have variable limits, we use the general Leibniz rule. Applying that, we get di by dt is equal to f of b of alpha comma alpha, that is f of t comma t, times dB by d alpha or dB by dt, which is equal to 1 minus f of a alpha comma alpha. Now that is f of 0 comma t times dA by d alpha, that is dA by dt, which is equal to 0, plus the integral from 0 to t of the partial derivative of f with respect to t dx. Now we have f of x comma t equal to 2x plus t cube the whole square. Now let's evaluate the partial derivative. Partial derivative of f with respect to t will be 2 times 2x plus t cube times 3t square, which is equal to 6t square times 2x plus t cube. Now the integral of this partial derivative from 0 to t is equal to 6t square constant times the integral 0 to t of 2x plus t cube dx, which is equal to 6t square times x square plus t cube x from 0 to t is equal to, if we substitute 0, the whole thing becomes 0. So we just have to take care of t. So substituting x for t, we get 6t square times t square plus t to the power of 4. And we also need f of t comma t. So f of t comma t is equal to, remember, it is f of x comma t. So the second t is already there. We are substituting x with t. So f of t comma t is equal to, instead of 2x, 2t plus t cube the whole square, which is equal to 4t square plus 44 plus t6. And now substitute everything into this di by dt. So di by dt is equal to, what is the first term? ft of t comma t. So that is 4t square plus 44 plus t6 plus the integral, that is 64. If we multiply these two or distribute, 64 plus 66. And simplifying that, we get di by dt is equal to 4t square plus 10t to the power of 4 plus 7t to the power of 6. So that is the desired integral. In summary, we can say another way to understand this is to look at d by dt of the integral from 0 to t of 2x plus t cube the whole square dx as the rate of change of area under the given curve, which depends on a parameter t. As t changes, the area under the curve changes. Now, the integral depends on t in two ways. Upper limit depends on t, which means the interval of integration expands as t increases. And the integrand depends on t, that means the height of the curve changes as t changes. In case of constant limits, only the height changes as t changes. In case of limits depending on t, the interval also changes as t changes. So that was differentiation under a definite integral, also called the Leibniz rule. If you found this helpful, don't forget to like, share, and subscribe. Questions, suggestions, and opinions are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.